Hello. In this module, we will start to discuss on how to design a controller using frequency response analysis. But before we start, I want to first discuss how to analyze behavior of a dynamic system based on the Bode plot of the system. Why a frequency response function is preferred? It's simply because frequency response function is very convenient to be obtained either experimentally or mathematically. And on the other hand, unit step response is also typically used to investigate the behavior of the system. If you still remember, in the previous video we have already discussed when we want to assess behavior of a dynamic system, we typically investigate it based on the response of some test signals. And one of the test signals is a step signal. So unit step response is the most convenient response to be used to understand the system's behavior. Therefore, based on these two statements, we are going to analyze the relationship between a frequency response function of a system to the unit step response. We will investigate it for two different types of problems. We will investigate on how the relationship of a Bode plot of a system, relationship of a Bode plot of a system to its unit step response. And in the second part, we will investigate how to correlate the unit step response of a closed loop system based on the Bode plot or the frequency response function of its open loop transfer function. Okay, in the first place, we will only take a look on how a unit step response will look like in relationship to its Bode plot system. You can consider this as a closed loop system, how the unit step response of a closed loop system is related to the Bode plot or the frequency response function of the closed loop system itself. So both are the same system. And in the second place, we will consider how a unit step response of a closed loop system is related to the frequency response function or the Bode plot of its open loop transfer function. Let's start it with the first one. We will find the relationship of unit step response of a certain dynamic system with its Bode plot. To start, let's just consider the following unity feedback system. The following unity feedback system, where the open loop transfer function GS, you can see it on the slide here. In such, if you evaluate the closed loop transfer function, if you evaluate this unity feedback system transfer function, as you can see, because what we have now here is a unity feedback system, therefore the closed loop transfer function TS will be equal to GS. I will write it G here because it's not easy to write it with my mouse. GS over 1 plus GS. This is the closed loop transfer function, will look like if G is the open loop transfer function. So in this unity feedback system, apparently we have a simple second order transfer function, where in particular here let's just consider a second order system where the DC gain is equal to 1, right? The DC gain K, if you refer to the standard second order transfer function, typically we have DC gain K, but then in this particular case, let's just consider second order system with DC gain equal to 1. In the following, we will later evaluate how the frequency response of this system will be in relation to a unit step of this closed loop system. In this particular video, we will just discuss the relationship of the Bode plot of a closed loop system, of a second order system, with its unit step response. We are not going to discuss it for ramp response. If you still remember, typical underdamped second order system, the unit step response will have at least 4 or 5 features that we can identify. You still remember this when we discuss second order systems in the previous few videos. The typical features on the unit step response are percent overshoot, settling time, peak time, price time, and probably delay time, right? So these are the features that we typically can identify from unit step response of second order system, in particular for an underdamped second order system. Since we are going to evaluate the relationship to the frequency response function of the second order system, it's pretty logical if we also have to identify some features from the frequency response function itself. So let's try to identify some typical features from frequency response functions in an underdamped second order system. If we have a second order system, in particular an underdamped second order system, the magnitude plot of the Bode diagram typically will look like this, as you can see in this slide, where at the beginning, when the frequency is low, at low frequency region, the magnitude plot will typically have zero slope, and at high frequency region, above the corner frequency, the magnitude plot will have negative 40 dB per decade slope. That's how we typically sketch for underdamped second order system. It should be at high frequency, the slope, this slope typically is equal to negative 40 dB per decade, right? You still remember how we sketch the Bode plot of dynamic system. And in most of the cases for an underdamped second order system, we can identify few features. The first feature is omega r. What is omega r? Omega r is the frequency for which the magnitude plot will be maximum. Omega r typically is more or less close to omega n, close to the corner frequency. And the peak here, the maximum magnitude in each Bode plot, is indicated as MR. So these are the two features that we can identify from Bode plot, in particular magnitude plot of a Bode diagram from an underdamped second order system. In fact, there is one more feature that we can identify from this Bode plot, which is referred to as bandwidth frequency, or we indicate it typically as omega b. What is bandwidth frequency? Bandwidth frequency is the frequency in our magnitude plot where the magnitude is 3 dB, 3 decibels below the magnitude at low frequency region. Okay, so in short, here we can identify three features from Bode plots of an underdamped second order system. On the other hand, we have already discussed before unit step response of an underdamped second order system. From this typical unit step response, we can identify at least 4 or 5 features, namely settling time, peak time, rise time, and percent overshoot. And if you still remember, in one of our videos, we conclude last time that these features, at least these 4 features, settling time, peak time, rise time, and percent overshoot, all of them, 4 of them, can be characterized by zeta and omega n. So TS, TP, TR, and percent overshoot, all of them are functions of zeta and omega n. If you still remember, also we have already discussed before that percent overshoot, in particular percent NP or percent OS, percent overshoot here, is only dependent to zeta. You can take a look again on that video that when we discuss the typical unit step responses of an underdamped second order system. You can find the formula that correlate percent overshoot to zeta. In short, percent overshoot is simply a function of zeta, while for the other features, settling time, TS, peak time, TP, and rise time, TR, these 3 features are dependent to zeta and omega n, dependent to both of these parameters, zeta and omega n, or they are dependent to omega and sigma, right? Where sigma is the real part of the pole, and omega or omega d here is the imaginary part of the pole in our second order system. Okay, now we are going to find the correlation between TS, TP, TR, and percent overshoot, percent OS here, to the features that we can identify from the magnitude plot of our Bode diagram, which are omega b, mr, and omega r. From the Bode plot of the underdamped second order system, or in the previous slides we referred to as a T j omega, omega b, based on the definition of bandwidth frequency, is the frequency at which the magnitude is minus 3 dB away from the magnitude at low frequency, at omega very small, close to 0. Considering our transfer function of the second order system, where the DC gain is equal to 1, the magnitude of T here, the magnitude of T at low frequency will be equal to 0 dB. Therefore, the magnitude at bandwidth frequency here will be equal to minus 3 dB. Okay, so from there we can easily identify the bandwidth frequency mathematically. Resonant peak, on the other hand, resonant peak MR is the magnitude value at the resonance frequency omega r. The bandwidth frequency omega b will tell us how fast the system will respond to an input. Therefore, if you see, if you are referring to a magnitude plot of the Bode diagram of an underdamped second order system, the wider this range, the wider the range where the magnitude plot is more or less flat in frequency, the wider that range, the faster the system will respond to an input. In particular here, for zeta between 0 and 0.707, we will have the peak of MR here. The higher the MR, the higher the maximum overshoot. Okay, so one thing that probably I need to mention now, this magnitude plot that I showed in the previous slide, also in this inside of this slide, is a particular case of an underdamped second order system Bode plot, where zeta is only between 0 and 0.707. When zeta is greater than 0.707, we typically don't see the resonant peak MR anymore. Okay, the peak is not so apparent when zeta is greater than 0.707. Now, in this slide you can see the relationships between the MR, omega r, and omega b to zeta and omega n. I will just show 3 formulas here. The first formula is the formula that correlate the bandwidth frequencies to zeta and omega n. The second formula correlates omega r, the resonance frequency, to omega n and zeta, while the third formula here correlates the MR to zeta. So pretty similar to the features of unit step response, where we have TS, TR, TP, and percent overshoot. In that case, TS, TR, and TP are characterized by zeta and omega n, while percent overshoot is only characterized by zeta. In the magnitude plot of an underdamped second order system, we have omega b, omega r, and mr, where omega b and omega r appear as a function of omega n and zeta, but the mr is only dependent to zeta. Okay, I will not discuss too much on how these three formulas are derived. If you are interested on how these formulas are derived, please refer to the appendix of these slides. You know how to find the copy of these slides. I have already uploaded the copy of these slides in Toledo. Okay, this just to give an illustration to you then how to correlate the features of a unit step response to the features of a Bode plot in our second order system. So let's consider I have an underdamped second order system where apparently after I give a unit step input to that system, the response shows 20% of overshoot. From the formula, one of the formulas that we discussed in the unit step response in our previous video, we can find that zeta or damping ratio is simply a function of percent overshoot here. If you need to refresh your memory, please refer to the previous video that explained the formulas to correlate percent overshoot to zeta. The formula will look like this, and then from this formula we can identify the damping ratio if we know the percent overshoot of a second order system response. So from this formula we know that if maximum overshoot is equal to 20%, the zeta will be equal to 0.456. And apparently the unit step response of this system, after I evaluate the response, the peak time is equal to 2 seconds. And again, from one of the formulas that we discussed before, peak time is characterized by zeta and omega n. You can refer again to the formula, and since we have already identified zeta, we can identify the omega n easily. So from these two features of our unit step response, we can translate the information of percent overshoot and peak time to zeta and omega n, where zeta in this case is equal to 0.456 and omega n is equal to 1.765 radian per second. Knowing these two information, we can easily estimate the features of the Bode plot. From the formulas in the previous slide, we can calculate the MR value and omega R value. If you want, you can also identify the value of omega B, the bandwidth frequency. Therefore, knowing these three features of of the Bode plot, of the magnitude plot in our Bode diagram, we can easily sketch the magnitude plot of the Bode diagram as well. Okay, in the next video, in the next short video, we will discuss on how to correlate the unit step response of a closed loop system, but now by looking at the open loop transfer function Bode diagram.